We will hear about ship ice fluid interaction studies on the ice resistance of ships. So, please.
Thank you. And thank you for inviting me to this very interesting workshop. My organization where I work is TRAFI, Finnish Transport Safety Agency, which is responsible for safety and pollution of prevention from vehicles, that is trains, air traffic and shipping. We are actually not a research organization, but we have a small in-house research department, and in addition to that we finance research related to our duties annually. I think our budget nowadays is something like a little bit more than 1 million euros in total. And here you can see my short CV. I'm a naval architect. I have been worked for 2 Finnish shipyards in the past, for a Finnish shipping company for a while, and for also I have worked at the Helsinki University of Technology, which is nowadays called Aalto University, as a research scientist. The link to this issue is that I have been responsible for the development of the Finnish-Swedish ice class rules for ship sailing in ice conditions at our administration. Research related to winter navigation has been done for a long time in Finland. It started in early 1970s. We have a so-called Winter Navigation Research Board, and annually a certain funding is given from the maritime administrations in Finland and Sweden to promote winter navigation in the Baltic Sea and adjacent sea areas. The research and development which we are funding should focus on the meteorological, oceanographic, technical and nautical conditions of navigation in ice. The research board announces a call on a yearly basis, usually in early summer, focusing either on parts of the above mentioned subjects or all of them. Currently our annual research budget is about 200,000 euros in total. Here you can see the contents of my presentation. I will first give a short introduction to the ice resistance problem, show a picture of ice conditions in the Baltic Sea area. I will discuss on definition of ice resistance of a ship, and 2 issues are the main subject. Firstly, studies on ice resistance in level ice, and then I will also present one study on ice resistance in brash ice. In practice, ice resistance of a ship can be determined by tests made in full scale, by tests made in model scale, by using calculations, by using empirical formulas, and also by using numerical methods based on physical models. Model testing and use of empirical formulas are important to ship designers, whereas the scientific community, of course, is more interested in developing real physical models. Full-scale testing is important, both for verification of empirical models and physical models. The purpose of my presentation is to present studies on ice resistance of ships, which are based on direct calculation methods, based on real modeling of physical phenomena. And ice resistance of ships in 2 types of ice conditions are discussed: ship ice resistance in level ice and ship ice resistance in a brush ice channel. In this picture you can see an ice chart made by the Finnish Meteorological Institute showing typical ice conditions in winter time in the Baltic Sea area. You can see Finland over there, Sweden, Denmark, Germany, Poland, the Baltic Sea states and the Russian Federation. And as you can see, in this case, all the ports along the Finnish coastline are surrounded by ice. And that is the reason we need several icebreakers to assist cargo ships to our ports during winter time. And also that is the reason why there has been a special interest in research of winter navigation in Finland. And the reason that the ice is usually packed against the Finnish coastline is that during the winter time southern and southwestern winds are the prevailing wind conditions. And that is the reason that usually ice conditions are heavier along the Finnish coastline compared, for example, to the coastline of Sweden. In these pictures we can see several different types of ice conditions which prevail in the Baltic Sea area. In the first picture on the upper row we can see ice flows at open sea, which is quite usual. There are no real obstacles for ships for sailing through that ice. But if there are ice ridges like here and level ice, the sea is totally frozen, then it's much more difficult to sail in ice conditions, and icebreaker assistance is really needed for cargo ships. In this lower picture you can see level ice which is formed in an archipelago area. You can see people skating there. There's even not much snow in this case on the ice, although usually, as you can see here, on the level ice there is a certain thickness of snow as well. And then in archipelago areas where we have fairways, we have also brush ice conditions. If you have a fairway and ships sail through the same fairway, during the winter time we get this kind of ice rubble, which consists of different sizes of ice pieces, usually with a rounded shape. And during the winter period more and more ice accumulates in the fairways, and that's a certain obstacle for shipping as well. So in my presentation I will first focus on ice resistance in level ice and then ice resistance in a brush ice channel. Then some words on definition of ice resistance of a ship. Ice resistance is defined to be the average resistance force on the ship sailing in ice conditions. In this picture we can see ice resistance data from full-scale tests for Russian icebreaker Vladivostok. These are the measurement points. We can see that there is a certain scatter in these results, and usually the ice resistance is assumed to be linear average of the measurement points. So the ice resistance is linear, at least with relative slow speeds, whereas the open water resistance curve as shown here is non-linear, especially at higher speeds. In Finland, usually the idea has been that ice resistance is separated from open water resistance. So if we have total resistance in ice, we subtract the open water resistance from the total resistance and get the ice resistance. This definition assumes that ice resistance and resistance in open water can be superposed, but actually this is not quite true, although the error might not be that big because the open water resistance usually at very slow speeds is not very high. So level ice seldom exists at open sea because the ice field is in continuous motion due to wind at open sea, but we have level ice in the archipelago area, and for ice-breaking ships, the highest speed of a ship in level ice is an important measure of the ice-going capability of the ship, and this is very often defined in ship's contract. For example, the ship may be required to break 1.2 meter thick level ice with a certain bending strength when the speed of the ship is 2 knots. This is a very typical definition in a ship's contract. And we can separate several phases in this level ice breaking process. When the ship is approaching intact ice sheet, the ice sheet is first broken. We call this breaking phase, and then this broken ice floe is rotated so that finally it leans against the hull. This is so-called rotative phase, and then after that the ship is gliding over this broken ice field, and we call this sliding phase. In this picture we can see the ship, which is this photograph is made underwater. We can see the ship bow here. The ship is advancing this direction, and we can see here that the whole ship hull is covered by these ice floes. This picture is taken in a model test tank. And as I mentioned, there are several means to determine the resistance of a ship in level ice. But now I will discuss on numerical methods to calculate resistance of a ship in level ice. Petri Valanto is made pioneering work in this field in the end of last century. And later on, Fernando Puntigliano made some tests and also a thesis on the issue concerning the sliding phase. And also I made my thesis in 2007 on the ice sliding resistance. Valanto made tests in 2 dimensions first, and here we can see time history, or actually this is the distance of the advancing ship, and here we can see the force when the ship is hitting the ice field and the ice is broken first. There's a huge force peak, and then this part of the figure represents the rotating phase, and the second force peak is generated when the ice floe hits against the ice the hull. So this type of forces occur in the ice breaking and turning phase. Later on, Valanto also made a 3-dimensional model so that the ice field was modeled by using the finite element method, and the ice breaking was modeled in this way, and then fluid mechanics was applied to model the flow of water below the ice field and the ship. So Walanto got certain results which did show very good relationship with full-scale data. We have full-scale data resistance points here, these red dots. The lowest curve is actually an empirical curve indicating the ice sliding resistance, and the other curves represent certain forces due to the ice breaking rotating phase and when the ice flow hits the hull and so on. So actually Walanto was able to model these phenomena, but he didn't discuss on the ice sliding phase, which still remained an unsolved issue at that time. Then later on, Puntigliano made model tests with a segmented model. He had a landing craft bow here, and he divided the model in several segments, and he had force transducers in these separate segments so that he could measure ice resistance for each segment. And also he had pressure transducers on the other side of the model where he could measure the pressure between the hull and the sliding ice flows in the ice sliding phase. Also some other people made similar kind of tests, and all tests made in model scale indicate that ice resistance increases in the ice sliding phase, and also the tests of Puntigliano showed that pressure in the gap between the hull and the ice flow decreases in the ice sliding phase. Now there are different theories indicating why the pressure changes in the gap between the hull and the ice flows in the ice sliding phase. It may be due to change of geometry of the hull when the ice flows, when the ship glides over the ice flows, and also inertia forces were indicated. I made a hypothesis in 1993 that inertia forces may be relevant or should have to be taken into account when pressure between the hull and the ice flows is calculated. And if there is a pressure decrease between the hull and the ice flow, we have this PD here. We have the static pressure, which is the lift of the ice flow leaning against the hull, and if the pressure is negative, pressure difference is negative between the hull and the ice flow, then we get higher normal force, and due to the higher normal force we get more frictional resistance, and that might be the reason for additional resistance due to the flow in the gap between the hull and the ice flows. This is a description of the ship ice fluid interaction problem, where we have the ship hull here, which was this is a section of the ship hull. It was assumed in my theoretical analysis that the ship hull would be a ball-shaped structure, and then the ice flow is rectangular, and in the middle of the ice flow there is the contact point between the hull and the ice flow. And then here we can see a section of this. The above figure, here we have the hull, and here is the ice flow, and there is certain flow generated by the movement of the hull above the ice flow. So the problem is to calculate what kind of flow actually exists in the gap. I started from the Navier-Stokes equations, which were simplified by neglecting the momentum equation across the gap, because the gap is really small compared to the other dimensions. And then the remaining equations were integrated across the gap when we get the equations of Constantinescu. These are actually equations used in lubrication theory for special type of lubricants where inertial forces and also turbulence have to be taken into account. Usually in lubrication theory the flow is laminar, because otherwise lubrication may not be constant. But in some cases, if we have special lubricants, this kind of theory would have to be used. So this is applied in this case, because clearly in full scale at least the flow in the gap is not laminar but turbulent, and inertial forces also will have to be taken into account. The CFD code was developed to solve the equations of Constantinescu numerically, and in these pictures you can see the calculated pressure field between the hull and the ice flow when the hull has a form of a ball and the ice flow is rectangular. And here we can see that partly we have a positive pressure difference here, but most of the pressure field is negative, so if we integrate the pressure field we get a negative pressure between the hull and the ice flow, which means that actually the compressive force between the hull and the ice flow is greater than what statical analysis indicates, and for that reason also the resistance increases. And this negative pressure drop increases when the speed increases, something like that. And then in this picture the effect of low pressure on ice sliding resistance of a rectangular ice flow is presented. And if it is assumed that the ice flow, the size of the ice flow is constant, then we go along this figure. But if we take into account that when the speed of the ship increases, also the size of the broken ice flows decreases, which is general observation in ice breaking process. This indicates that the increase of the ice resistance is more linear compared to the assumption that the ice flow, the size of the ice flow is constant. So in this way it is shown that in principle this phenomena may have an effect on ice resistance in the sliding phase, and it may also be that the increase of resistance with speed is linear, as indicated by empirical studies. So the conclusions of this analysis is that the inertial forces due to fluid flow in the gap between the hull and the ice flow may cause decrease of the pressure in the gap. Change of the pressure may also be caused by change of the geometry of the hull, and the low pressure phenomenon should be taken into account when ice sliding resistance is calculated, because the normal force due to the decrease of the pressure and frictional resistance due to this force in the contact point between the hull and an ice flow may be several times higher than the force due to static lift of the ice flow and frictional resistance due to it. This long sentence summarizes these conclusions. And of course there are some topics which require further research. In this picture you can see a ship model, and there is a window in the ship hull, so that when the ship is breaking ice in model basin, we can see through the window the broken ice flows here. And here we can see that there are gaps between the ice flows, and I think that the effect of these gaps between the ice flows on the pressure field between the hull and the ice flows should be further studied. And then there are several other things. Of course, more pressure measurements should be made in full scale. Now we have only one set of measurements in full scale made by Puntigliano. Perhaps more tests should be done with segmented models. And then there are other issues. Normally there is snow on level ice, and what is actually the effect of snow on ice resistance in level ice. And then air bubbling, the effect of air bubbling on ice resistance. In the past, air bubbling systems were used in ice-going ships, which means that air is compressed, is directed by compressors below the waterline of the hull of the ship into the water, and the idea was to decrease the resistance of the ship in ice in that way. So that is one problem which could also be analyzed numerically. So that was all on ice resistance in level ice, and then we turn to ice resistance in a brush ice channel. In this picture we have a view on a fairway which is full of brush ice, which may be even several meters thick. This issue is actually related to the Finnish-Swedish ice class rules. The Finnish-Swedish ice class rules consists of three issues. Firstly, we have minimum propulsion power of ships in our regulations, and then strengthening of the hull and the propulsion system against ice loads. We have four ice classes, 1B, 1C, 1B, 1A and 1A Super, which is the highest ice class. And according to the minimum propulsion power regulations, a ship having a Finnish-Swedish ice class should be able to sail independently, that is without icebreaker assistance, in a brush ice channel at a speed of 5 knots. The idea behind this definition is that because there are plenty of cargo ships annually in wintertime in need of icebreaker assistance, the authorities would like that cargo ships having an ice class should be able to sail in fairways in archipelago area without icebreaker assistance. So that is the reason for this this definition. It is clear that at open sea, where there are no ice channels, of course, because the ice field is constantly moving, icebreaker assistance may be needed if there are ridges or level ice, or if there is ice compression at open sea. Now the minimum engine power can be determined by using analytical formulas which are given in our regulations, by using model tests or by using direct calculation methods. Model tests have been done and the ice class and propulsion power of the ship has been accepted by the authorities based on model tests, but so far direct calculation methods do not yet exist. And in this figure we can see that we have defined certain thickness of the brash ice for different ice classes in the middle of the ice channel. This is half of the ship and this is half of the ice channel, and the idea is that this is the intact channel, and then when the ship is passing through the channel, the brash ice would be compressed aside by the side of the ship. Usually the ice channel is very thick in the boundary area because the ice tends to get thicker here, and also which makes that the brash ice is not, it's assumed that the brash ice is not able to be moved sideways below the ice, but it is compressed by the side of the ice channel between the ship and the side. Now we financed one study made by VTT, by Sorsimo and some other research scientists to simulate the ice resistance of ship in a brash ice channel. They used the discrete element method, and the real geometry of the hull of existing ship at that time was used in calculations. In the simulation, the ship was moving unidirectionally in a brash ice channel, and the geometry of the channel was modeled according to the rules. And the brash ice in the channel was modeled by a huge number of ice particles with a spherical shape interacting with each other and with the ship. Forces related to gravity, buoyancy, inertia and contact forces including friction, as well as fluid drag using a simple formula, were taken into account in the simulations. And also a slight freeze bond between the particles was generated to mimic the cohesive forces found in reality. Now the results indicated that the simulation of brash ice failure process was visually realistic, corresponding to the full-scale observations. But however, the calculated ice channel resistance was substantially lower compared to the analytical study. The reason may be that the major lack in the model relates to the model of brash ice and the evaluation of the material parameters, because the current parameterization which the scientists used refers to the ice rubble in ice ridges. And as the brash ice in a channel was created by spherical ice particles of the same size, the porosity also was higher than observed in experiments. That made brash ice looser and therefore weaker, which also caused that the implementation of the cohesive freeze bond between the particles didn't produce any notable effect on the channel resistance. But however, as the user can model real ship geometry and define the channel geometry and material parameters of ice without considerable restrictions, we think that this DEM methodology itself is is a promising basis for further development. And then we come to conclusions. We can say that physical models to calculate ship ice resistance in level ice have been developed, but a complete calculation model does not yet exist, which would be able to calculate the total ice resistance due to the ice breaking process. In practice, empirical models are still used to calculate ship ice resistance in level ice. And then the discrete element method has been applied to simulate the ice resistance of a ship in a brash ice channel. However, the physical model still needs to be refined in order to get satisfactory results. So the scientific community is invited to further develop the ideas introduced in this presentation. My idea always has been that we should leave some research also for future generations, and for that reason the world is not complete yet. There is plenty of space for people to continue this field and work in this field and hopefully get even better results. And also I can say that you can easily be in the top 10 research scientists in this field, because there are not 10 scientists in this field. You can easily be even a leading expert in the whole world, so it might be wise to choose your object so that you are the leading expert in the world. And then I would also like to mention that some funding for this kind of research is annually granted through the Winter Navigation Research Board by the Finnish and Swedish maritime authorities. Very often our research is more practically oriented, but we have also financed some academic research in the past. And then I have mentioned, I have listed some important references also in the end of my presentation. There are my studies of Puntigliano and studies of Valanto concerning level ice resistance, and then references to studies on ice resistance in brash ice, which are available at our website also. And actually you can find almost 100 publications there which have been produced during the past 45 years, which have been funded by the Finnish and Swedish maritime authorities. So please feel free to visit our website. And this funding is also announced at our website, so you can find more instructions there if you are interested. Thank you for your attention.
Yes.
Thank you for a very enjoyable talk. You showed some solutions in the middle there by Konstantin, somebody other, of the good of the boundary layer equations, essentially, between ice and the hull. I just wanted to ask, have you got any velocity profiles that come out of the system?
You mean this one?
More. Maybe the next.
A bit further
A
on.
bit further, yeah. Here, yes.
Yes, those, yeah. So it's the nonlinear lubrication equations, or I guess the boundary layer equations.
Yeah.
So do you get velocity profiles out of that? And is there sort of flow reversal?
Sorry, I didn't get.
Do you have any flow separation? That's maybe your question.
Oh, flow separation.
You have the flow separation in this interaction with the flows?
No, these equations do not take that into account. The gap really has to be small enough in order that these equations apply.
But you can have flow reversal. That was the question.
Yeah, that is one possibility also, and that's one important issue which should be also studied further. I didn't really study that in detail in my analysis.
You've got, I see a nice adverse pressure gradient, favourable, and then adverse, which suggests there might be flow reversal on the sides.
Yeah, that is a valid point, really. Yeah.
Question there.
Thank you for a very nice talk. So I was quite struck by the photograph of the flows on the underside of the sea ice, underside of the ship. And I had a very naive idea, which you'll probably tell me is wrong. I was wondering if you'd designed the bow of the ship to be concave near the front. When the flows go underneath the ship, they could be steered away from the underside of the ship, so they wouldn't collect like that, and that could reduce the sliding resistance. Is that a possibility?
Yeah, of course. It depends on the ratio of the dimensions of the ship. I mean, what is the beam? How deep is the draft of the ship? It depends whether or not the whole hull is actually covered by ice. Usually, probably, if it's a bigger ship with a deep draft, it may be that only you can see ice pieces on the sides of the ship, not on the bottom area, really. So the ratio of the main dimensions, beam and draft, is important with regard to how it looks like. But actually this has been also verified in full scale. In 1960s, when the issue was studied first time, people had an icebreaker and then they sailed in level ice, stopped the ship and sent a diver down there to look with lights how it looks like. And they explained that the ice floes were really leaning against the hull, just like in the model scale.
But if you had a concave hull, could it steer the flows away from the ice?
Yeah, there have been different kind of hull types tested, and if you have a very wide bow, it may be that actually, I mean, there have been ship designs where the short distance of the bow is wider than the ship in the midship, for example, which means that in those cases it may be a different kind of coverage of ice flows along the hull.
Okay, two more questions. Yes, please.
Yeah, I wonder how do the Russians study this problem? They have a lot of icebreakers.
Yeah, ice research is mainly done by Finnish scientists and Russians, of course, and Canadian. In Canada also, and in some other countries. I think in Russia they have mainly made empirical formulas. We have the Castellian formula, choice formula, Ionov formula. In my first study, which is on the list of references, I think I have listed 30 or 40 different formulas, empirical formulas, I mean, to calculate ice resistance of a ship.
Yeah, my question about brush ice. You use the you modeled that ice by spherical particles, many of them.
Yeah.
But did you try, or do you think it's reasonable to model it by, say, layer, viscoelastic layer, or another with other conditions, like it was explained by Haley Chen, who asked you the previous question. So she showed that another model, the kind of the brush ice is considered as a continuum media with the certain characteristics instead of many particles. So do you think it's reasonable, or?
I think it might be easier way actually to do to analyze the issue if you are able to determine the material parameters for this brush ice, because these computational models I've seen also other studies related to it, and what I have shown here, they easily tend to require a lot of computational capacity. You may have to run your computer for days in order to get some results. So that might really be one way to try to go ahead. But of course, when computers and the programs get better and better, it would be interesting to continue this way as well. So difficult to say. Yeah.
Okay, I think we are a little bit over time, so I think we stop here. So thank you once more to Dr. Kämäräinen for this lecture.